Hi, in this video we'll be talking about caching and how we can leverage this concept to improve performance of our web application. Any business operation which our application performs can be written down as a combination of compute and storage. It is at a very high level, we collate information from a bunch of data sources. Maybe most of it is in our databases, maybe some of it is static content, and some of it is fetched through different systems through API calls, and we perform transformations on this data and return it back to the user. Most business applications can be written down in those terms, and Cache tries to optimize this process by storing or pre-computing a lot of frequently accessed business operations in a faster mode of storage. Let's take the example of a simple read from DB. Let's say we have a business operation which performs a rather complex query on the DB side. It's a join, let's assume. In a naive implementation, what's going to happen is that the server is going to make the query to the DB, which has the data stored on disk. The information is retrieved rather in a slow manner and sent back to the user. And if the same operation was performed like 10 times per second, then the same thing would happen 10 times over. And Cache here is trying to optimize this process by storing this frequently accessed piece of information in a faster mode of storage, maybe on an SSD or even in memory. So the first time the user requests a particular business operation, it's going to happen naively. The DB is going to serve up that information, but a cache entry is going to be made. And the next time the same query is performed, it's going to be fetched from the cache, and that's going to put less strain on our key resources. The DB utilization will go down because of this. That's one example of leveraging caching in our application design. Cool. So in more general terms, caching is just pre-computing commonly performed operations and moving data queries of frequently accessed data from a slower form of storage to a better form of storage, maybe from disk to in-memory or maybe even SSD. One of the fastest ways of retrieving data is through L3, L2, or L1 caches, but that is abstracted away from us, and we don't have, as developers, we don't have access over the data stored in caches. But that's something which sits on top of the hierarchy, which has the least latency, but also is really expensive. So what do we cache? We cache DB results, as exemplified by our complex SQL query example. We cache computations. An example would be how Google performs PageRank on the documents and website it crawls. It pre-computes the inverted index data structure as a batch process beforehand and stores it in a data store so that it doesn't have to be computed each time a request comes through. That is a form of caching as well. The third type of content we cache is static resources like videos, music files, documents, HTML and JavaScript, static websites. All of those are candidates for static caching. A popular implementation of static caching is CDNs, which we will discuss later. A complication which maybe I'd like to discuss with DB results in particular is two ways of caching content in the DB. One way is we cache most frequently used queries For example, there is a select statement or maybe a join statement. We take the query string and we calculate a hash, and we store this key value pair where the key is the hash of the query and the value is the result, and we store this key value pair in the cache. This is one rather intuitive way of caching DB results, but there are problems with this. There is no easy way to identify which cache entries should be invalidated when a write happens to the DB and an underlying value is updated, which will have cascading effects into these values. There is no easy way to identify which cache entries will be affected in each write. And because of that, we have to fall back to invalidating the entire cache every time a write or an update happens. And that can be suboptimal for your use case. Maybe a better way to cache DB results is that you cache each record as an application layer object. Let me take an example of a Spring application. In Spring applications, if you have used it, there is a representation of each record in the DB in the form of an entity object, an application level object. So one way of caching DB side records would be to store them as application objects in the cache itself. Cool. Let's move on to the different modes of caching. One of the simplest ways, and something which is ubiquitous across all the applications you visit, is storing static resources at your client side. You might have noticed that if you open YouTube when you don't have a network connection, you are still greeted with a YouTube UI. And that is because a part of the YouTube website is cached in your local setup. So client-side caching of static resources is really popular. Web server, the backend server which is catering to your request, can also have data stored about you in its memory. And this is really easy to set up, but the problem here is that if you start storing information about your users in your web server, then you introduce stickiness. Then the next time the user fires an API call, we have to make sure that it enters the same web server and not some other one in your horizontally scaled infrastructure, because only one particular web server will have the relevant cache entries for you. So this, along with session stickiness, if we are able to have that incorporated in our architecture, is a really great way of caching small data points about your customers. CDNs, content distribution network, are an excellent way of caching static resources. CDNs bring two advantages for you. One is that you can have infrastructure, commodity hardware, which is specialized in serving static resources, maybe through having better storage hardware. That's one. So we can have better hardware for serving static resources. The second advantage is that we can have the option to move the CDNs to edge locations around the world. Say your customers are coming from China and your main server, your key database, is in the Americas. Because of the sheer distance between the two countries, the network packets have to travel a long way, and this can introduce latency. CDNs allow you to have static resources cached across the world. Maybe there is a CDN edge location within China which can serve as a cache, and the customer won't have to make network calls which propagate all the way across the world. It can all be a round trip within China. So location advantages. The fourth way is through specialized caches, distributed caches, in memory caches like Memcached and Redis and Oracle Coherence, which store key value pairs entirely under the control of the application and the developer. And the last option is DB side caching. This is the most easy to set up. You don't need to change anything in your application. Your database administrator can change a few configurations, and that can magically net you a lot of performance improvement. So this becomes a really attractive option if you have built your application without keeping caching in mind, but you're still hoping for some improvement of performance. Then you can enable DB side caching and magically see a huge performance improvement. Let's talk about cache writing strategies. The most naive and simplest way of writing with a cache architecture is to write around the cache. What this means is all of your writes are going to be directed to the main database, and the cache is just going to not be part of the write process. There are two subcategories of write around. One is, let's call it a YOLO approach. The second one is a cache invalidation approach. If your application is fine with eventual consistency, then you can go with the YOLO approach. You just write data to your database and forget about it. That's the only thing you do. But the problem here is that there could be entries in the cache for a particular key. Let's say you're writing x equal to 10 from x equal to 9. So what is 9 becomes 10, but there is a cache entry for x which states that x is still 9. Now there is an inconsistency. The new write, which has only been made to the DB, says that x is equal to 10, but the cache entry from a while ago still says that x is 9. The next time x is queried, a read operation is performed on this key, the cache is going to it's going to register a hit, and 9 is going to be returned, and this is wrong. And the same stale data is going to be served till the time this cache entry is alive. Maybe the TTL, the time to live for this cache entry, is till Tuesday, and today is Monday. So for a whole day, stale data is going to be served. Only on Wednesday will this be updated to 10. So if your application is fine with eventual consistency, then you can go ahead and YOLO it. But if not, then a different way of ensuring some sort of strong consistency is through invalidation. So every time you write data, so you change x from 9 to 10, you invalidate the cache entries against x. So this will be deleted. The next time x is read, it will realize that there is no cache entry for x and it would be a cache miss, and you'll fetch the new fresh data from the database. The next approach is called write through. Here you write to the cache, but also within the same transaction you ensure that the data is stored to the DB. You can consider this to be a combination of write around plus making an entry to cache. So it's just two writes, one to the DB, which is write 1, and write 2, which is to the cache. This is good. This ensures that the cache and the DB are strongly consistent. There is no mismatch of information between the two sources. But the problem here is that you are making two network calls, so it's going to be slow, and you have to incorporate some 2PC, two-phase commit protocol here to ensure that both of these writes are successful, which is further latency introduced into the system. Because if you add 2PC, you'll have to make uh, a write call, then you have to make a check call to see if that both the data sources are ready to commit, and if both of them are, you have to give a go ahead. So 6 network calls instead of the earlier 2. So it's super slow, but it gives you the strongest consistency. The third strategy is called write back. Here your writes are just going to be made to the cache. You're not interacting with the DB in this situation. Let's say you write x is equal to 10, y is equal to 5, z is equal to 2 or maybe 3. All of these writes are going to be made to the cache, and they're also going to be added to a queue, and they're going to be batched. Once this queue reaches a threshold, or maybe a time period passes, all of these records which have been batched are going to be persisted to the DB at once. The benefit here is that this is super fast. This is probably, this is definitely the fastest out of the 3 write strategies, because you're writing to the cache, which is inherently fast. The problem here is that if the cache goes down, there is no way for us to retrieve the information. You have to ensure that the cache is replicated because of that. Or maybe the queue is redundant. So this information is stored in multiple queues at the same time to ensure redundancy. And there are problems with data consistency as well. Let's say you have a different user who is using the same system through a different cache, but this write, which has been performed in a different cache replica, has not been propagated to this one yet. So there are all sorts of challenges in ensuring consistency in such a system. Cool, that has been it. Thank you for watching.